Yeah, it was, yeah, in our project flow and our international methodology course, I remember.
We ran a field over 2019 for our
Okay.
students, and we came and gave talks and you
True,
took
we
us to
met
dinner,
again.
and then everything went crazy.
And then.
We have dinner in the museum.
Yeah, with all our students, so us,
Yeah,
so
yeah.
it's great. We're doing that again in November. Fine.
Yeah, things are fine. Here we lost some professors, not in the geology, not in the mining, but in other universities. Okay, we're here again.
Yes, okay, I'm speaking English. And I'm just talking English, it's not being translated. Tell me if I'm talking. I get excited.
Ya sea virtual a través del Zoom o presencial aquí en la Pontificia Universidad Católica del Perú. Mi nombre es Renber Condori Cutipa, del PUCP-UNSAAC, Joint Student Chapter. Y
Bueno, mi nombre es Ivana Cárcamo, soy vicepresidenta del PUCP-UNSAAC Joint Student Chapter. Y esta charla de hoy ha sido organizada en conjunto con la SGA Perú Student Chapter. Y nos es grato presentar a nuestro ponente invitado, el doctor David Cooke, quien nos va a hacer una presentación titulada Understanding or Forming Processes to Lead to a Discovery.
Yes. David Cooke es director de CODES, Centro de Depósitos Minerales y Ciencias de la Tierra de la Universidad de Tasmania. En colaboración con sus estudiantes, becarios y colegas investigadores, David investiga los procesos hidrotermales y magmáticos que conducen a la génesis de yacimientos de tipos de pórfido de cobre, desarrollando nuevas herramientas de exploración geoquímica para la industria minera.
David Cooke es editor asociado de Economic Geology. También ha recibido medallas como el Haddon Forrester King en 2018. También ha recibido la medalla de plata de la Society of Economic Geology en 2013 y el premio al conferencista Thayer Linsley en 2005. Bueno, gracias. The public is all yours.
Okay. Muchas gracias. Okay. I'll drive through here. Okay. Might use this. This good? Okay. So people online can see. Okay. Okay. You want the microphone? All right. Thank you so much for the invitation to come back to PUCP. It is always a pleasure to come here and meet with you and see Sylvia and Lizard and all of the amazing students who study here. I'm thrilled to be back once again in Peru after 4 years. Today, I'm going to talk to you about understanding ore forming processes in hydrothermal systems. And the reason I'll talk to you about this is that understanding is a really vital part of making discoveries of mineral deposits. Ore deposits form by certain processes at certain times in Earth's history. And so understanding when and how those processes occur and why they might lead to ore formation is a critical part of being able to be effective if you work in mineral exploration. Here, we are looking at an example of an ore deposit from southern Peru. This is Chalcobamba in the Las Bambas district of southern Peru. And this student of mine, former student of mine, James Cannell, who now works at Las Bambas as an exploration geologist, is very, very happy because in this case, we can see that ore forming processes have worked very effectively. We have what used to be a limestone. It has been converted to a marble, and hydrothermal fluids have reacted with it to produce garnet skarn and magnetite skarn. And in that magnetite skarn down here, all of this yellow material is chalcopyrite. So this is high-grade ore, And in this case, the ore forming process was an acidic magmatic hydrothermal fluid carrying copper, reacting with the limestone, dissolving the limestone and precipitating new minerals, magnetite and chalcopyrite after garnet. Very effective ore forming process with pH neutralization, so neutralization of acid by reaction with limestone. Just like when you're testing for calcite in the laboratory, when you put hydrochloric acid on calcite and it fizzes, that process with high temperature fluids can make an ore deposit. Before I go into detail of the different chemical processes and physical processes that may lead to ore deposit, the Society of Economic Geologists did ask me to just let everyone or remind everyone that their annual conference is coming up on the other side of the world in August this year in London, the United Kingdom. And student chapters always have the opportunity to go to these conferences. You can be applying for funding from the Society of Economic Geologists to participate in a conference like this. So they are wonderful networking experiences, and they are wonderful opportunities to learn about ore deposits and about what we do in researching ore deposits. Our Society of Economic Geologists conferences always have exciting field trips associated with them. And you can see this year, there are field trips to Spain, to Saxony, Bohemia, looking at the Cooke in Poland, going to Ireland, Ferroscandia and Cornwall. So these trips are great opportunities for students to learn about different types of ore deposits in diverse environments and to meet with other people from academia, from industry and from government, and to grow global connections that help you in your career. So if you get the opportunity to go to such a conference, grab it, seize it, because they are wonderful. They also offer things, workshops. And as you can see here, there are going to be 10 different workshops offered at this year's SEG conference. So fantastic opportunities to go to this. I hope that next week, some of you are also coming to the Pro Expo conference, the local opportunity to do these things as well. They're always great opportunities to meet people and to learn. All right, that's my advertisement. Now moving back on to talking about ore deposits. I don't know if you're familiar with the concept of mineral systems, but the idea of a mineral system is that we think about all of the things that have to come together to make a hydrothermal ore deposit. And so these can be a very large area of the earth to be thinking about. It could involve not just the environment, but all of the underlying crust and even things coming from the mantle when we're dealing with ore deposits associated with magmas. So this diagram, which was put together several years ago by some Australian geologists, is a concept that some mineral explorers and some researchers use to try to think about all of the elements that must come together to make an ore deposit. So we need to have an energy source that is driving ore formation. We need hydrothermal fluids, so hot water that has the capacity to carry metals and essential elements for forming ore deposits, such as sulfur, because often our ores are sulfide minerals. So we need a source of those ligands like sulfur, salt, and the water itself. We need a source of metals as well. Now, these may all be the same thing. They may all be coming, say, from a magma in the mantle, or they may be coming from a sedimentary basin that has a highly saline water due to the presence of evaporites. Different ore deposit types and different mineral systems will have different energy, fluid, ligand, and metal sources. We need to transport these from the source regime along fluid pathways through the Earth's crust to the site where the ore bodies form. So we need permeability. So we need ways for fluids to flow, and that might be faults and fault systems. It might be permeable aquifers. It varies from deposit to deposit. And then those fluids need to be focused into a small area where we might form high-grade ore. So these ore bodies will form by a conjunction of physical and chemical processes, and they need to work in an optimal fashion to produce your ore body. And the thing is, those processes are different in different ore deposit types. So you need to be able to understand a variety of possibilities to produce the ore bodies that we see today. The fluids pass through the ore environment and they produce alteration halos around the rocks. And that's essentially the spent fluid discharge. That's where once the metals are removed from the fluids keep going and they just leave a distal alteration halo. And in mineral exploration, we are often working from this area, trying to follow that alteration back to find the high-grade ore body. So if you work as a mineral explorer, you spend a lot of time looking for this from here, but you need to think about this to be able to predict where to find the ore bodies. So that's a quick summation of all the different things we might work on, going from crustal scale to district scale to deposit scale, so working across scales. Now, hydrothermal ore deposit types are many and varied. Some are associated with active volcanism, some are associated with sedimentary basinal processes, some form on the seafloor, and there are other environments as well. I'm not going to go through them all, but if you can understand the processes that can potentially operate in a given environment, such as this active volcano, where native sulfur is precipitating in great concentrations on the walls of the crater. This was a mine. They were mining native sulfur here, and 3 times the mine was destroyed by volcanic eruptions in the last 100 years. So very dangerous mining place. But the process there forming the sulfur is condensation. Sulfur from magmatic gas condensing to produce native sulfur. So there's a variety of processes that might go on to produce your different ore types. So here's some of the processes that it's important to try to understand. And I appreciate with the students here, we have a range of experiences. Some of you in second year, some in third year, some are master students. So these terms may be familiar to some of you and not so much to others. And also, depending on how much chemistry you've done. But in ore forming environments, there are several things we generally encounter. There is usually a temperature gradient between the fluids that are coming into the ore environment and those are going out. So there's the potential that the fluids will cool. And you can ask, could cooling produce high-grade ore? In some environments, the fluids might be heated. If you intrude a magma into groundwater, the water will heat up. Can that produce ore? Pressure changes are very important in certain ore environments. So as fluids are deep in the earth, they are under high pressure. If they migrate towards the earth's surface, they're experiencing lower pressure, and that can cause them to precipitate metals. So pressure change or decompression in particular, rather than increasing pressure, may be an important ore forming process. Water rock interaction. That's where a hydrothermal fluid reacts with the surrounding rocks, can produce high-grade ore. We saw one example with the first slide, and that was carbonate rocks reacting with acid fluids to produce what we call skarn. There's also processes of sulfidation, where we precipitate sulfides from hydrothermal fluids due to reaction with rocks. Oxidation and reduction can be very important as well, along with neutralization. There are some processes whereby metals may be sorbed onto or into pre-existing minerals. So gold might diffuse into pyrite or get attached to the surface of pyrite, and that can be an ore forming process. And then there are various ways that a fluid can transform from a single fluid into 2 fluids. You're all familiar with boiling, where water transforms to steam. We go from the liquid state to the gaseous state. That's a form of phase separation. If ever you have a cerveza or a Coca-Cola, you are experiencing effervescence, where CO2 dissolved in water under high pressure physically separates from the water when you release the pressure. That can be an ore-forming process. And there's another one we call, well, it's a tricky one. Different people call it by different names, but I'm going to call it unmixing. And that is when a high pressure, high temperature fluid that is supercritical, not water, not gas, but some intermediate density, comes to lower pressure conditions and physically separates into a salty water and a low density gas. All of those can be important for ore formation. You can condense gases as well, and you can mix fluids together. So let's look at each of these in a little bit more detail. I'm going to start with cooling. And the reason I want to talk about cooling is because quite often when people are trying to interpret how ore deposits form, they will say, oh, it formed due to cooling. And the reason they say that is because metals are soluble in most cases at high temperatures and high salinities and are less soluble. We can dissolve less of them in the water at lower temperatures. This graph on the left, you can see these are different metal species. That's uranium, zinc, lead, silver, manganese and iron, and they're all having solubility decreases as temperature decreases. And this axis is a log scale. So every tick, you are decreasing the solubility by an order of magnitude. So you look at that and say, well, maybe cooling is an effective method of producing high-grade ore. But the challenge is, how do you cool from 300 to 200 degrees in a small space? So we're going to look at that in a little more detail. And I also want to note for you that sometimes some things don't necessarily become less soluble on cooling. They may become more soluble. Here's a couple of gold species as bisulfide. And if nothing else changes, gold is actually becoming more soluble as these species as temperature goes down. Then, so you basically dissolve gold from the rock rather than precipitate it. So something else has to go on to make gold precipitate. That species won't produce gold just by cooling. So those ones could theoretically precipitate by heating. Don't think that happens. So the place on planet Earth where we get our most extreme temperature gradient is in submarine hydrothermal systems where high temperature fluids vent into the ocean. The hydrothermal fluid, and you can see it coming out of this black smoker here, has a temperature of about 350 degrees and the surrounding seawater is 2 degrees Celsius. So as this water comes out, it decreases in temperature by several hundred degrees in a very small space. And this is the most efficient ore forming process we see on the surface of planet Earth. It produces massive sulfide mineralization. Volcanic hosted massive sulfide deposits such as Cerro Lindo or Paruba here in Peru. And that black material you see here is all sulfide minerals precipitating from the hydrothermal fluid. But the thing is, temperature change isn't the only thing occurring here. There's also, because this is fluid mixing, there's an oxidation of the hydrothermal fluid as it mixes with oxygenated seawater. There's a salinity decrease. And because seawater has a pH of 8, there's a pH increase. So as with all ore forming processes, there's a competition between several processes. Some of them may favor metal deposition. Some of them may impede metal deposition. So it gets complicated to sort it through. But in this case, such an extreme temperature gradient is a major driver for ore formation. But it's not that easy to get that temperature gradient. Here is a near boiling hot spring in New Zealand. This is Champagne Pool. I don't know if you've heard of this place. It's very famous. because all of that orange material you see here contains gold and silver precipitating at the Earth's surface from this near boiling water. We might come back to talk about this a little bit later, but the key thing here is this water is 70 degrees and it cooled from 300 degrees, but that cooling occurred over 1 kilometre vertically. And so it wasn't very efficient. And it's only in the very upper part of the Earth's crust that we got some reasonably rapid cooling, 100 degrees of cooling over a 100-metre vertical interval. Whereas in the black smokers, we saw 250 degrees of cooling in the space of centimetres. So the temperature gradient isn't that great. Now, all this white material you see here, this is siliceous sinter. And around hot springs in high temperature geothermal fields, this material is very common. And that is because silica minerals, quartz, chalcedony, cristobalite, opal, amorphous silica, these all precipitate due to cooling and they form, as you can see, we can form them at these sort of temperatures and we're getting a decrease in silica solubility for quartz of about 600 parts per million as we go from 300 degrees to 100 degrees. When we get close to the Earth's surface, if we can cool quickly, we can supersaturate with quartz, and that's why we then get minerals such as chalcedony and cristobalite, and they are what form this material here. This is siliceous sinter. These are actually microbial mat material that's being fossilized by the sinter, and this is chalcedony intergrown with quartz, a bit deeper down in an epithermal vein. So cooling produces quartz and other phases, but it struggles to produce high-grade ore in many systems. I won't necessarily brood on this. I just say that there is also a salinity impact on all the processes we're talking about. And with regard, quartz and its polymorphs, high salinity can impede the precipitation of some silica minerals. May the 4th be with you. So cooling produces quartz veins. Every time you see beautiful coarse quartz crystals like this, that's a logical product of slow cooling of a hydrothermal fluid. Okay, there's a prolonged period of gradual growth of these crystals from a fluid carrying silica. Very pretty, but not ore. So when you see things like this out in the field, these little dilational tension gashes filled with quartz, they're not going to have any ore in them. They just have quartz precipitating due to cooling, maybe a bit of decompression as well. Now, why we do need to think about cooling in looking for ore deposits is because cooling controls metal zonation in and around hydrothermal systems. I've shown you that metal solubilities decrease with decreasing temperature. That's also true with decreasing salinity. And so around ore deposits that form in association with magmas, such as the porphyry copper deposit family or the granite-related tin tungsten deposits, we commonly see a pattern of metal zoning that is produced by cooling of the spent fluid going out from the ore body. And we use that metal zoning to explore and find the ore deposit in its center. So on the left, this is a little graph just showing you several metals and how their solubility decreases by orders of magnitude over a particular temperature range, quite a large temperature range. This diagram had to be drawn assuming a pH, an oxidation state, a total sulfur state. So there's a lot of things going on in the background to draw that diagram, but it just gives you the general feel of how temperature decrease can affect metals, especially metals that are dissolved as chloride complexes. So they bond with salt and move around in high concentrations at high temperatures. So granitoids have a particular zoning pattern, and generally there are some metals that we call proximal pathfinders that occur close to the granite, and some that we call distal pathfinders that occur far away from the granite. Now, whether the granite is oxidized or reduced will impact on the proximal pathfinders. So reduced granites, ilmenite series granites or S-type granites, these produce tin and tungsten deposits. So their proximal pathfinder metals are tin and tungsten. Porphyry copper deposits are associated with oxidized granites, or what we call magnetite series granites or I-type granites. And we see iron, copper, gold, and molybdenum in their core. Distal to both types, we see these elements: lead, zinc, manganese. We also get silver and gold distally as well as proximally, because gold can move both as fluoride complex and bisulfide complex. And there are regular patterns defined by these that we can use in exploration. So here's an example of a tin granite system in Tasmania, which is where I'm from. So this is the Renison Bell tin deposit and the surrounding Dundas mineral field. So Renison Bell is a Devonian granite-related carbonate replacement deposit of tin and lesser copper, and it is located here. And the granite is close to the surface underlying here, but Renison is hosted in a sequence of Proterozoic dolomites that are reactive rocks. And you can see all around here, there are numerous mineral prospects that contain tin. And then we have a halo around them where the dominant metal is copper. And we've got a second tin zone with a copper halo. And then distal to that is a zone of lead, zinc, and silver veins, essentially intermediate sulfidation epithermal vein systems. And so we see this metal zoning, and it's around where the granite highs are located. Okay, so there's our tin zone, our copper zone, our silver, lead, zinc zone. And just look at the scale bar here, 3 kilometers. So this is a 15 kilometers by 10 kilometers, or maybe it's 20 kilometer by 10 kilometer domain of many mineral deposits that have been forming. And the zoning we see here, the metal zoning, relates to cooling of the fluid as it comes further away from the granite. Okay, and just looking in the subsurface, here is Renison. You can see the ore deposit in red, and you see the granite, which has been intersected in drilling and deep mining, is sitting a good kilometre below the surface, and that's about the depth here. And then the granite gets deeper and deeper as we get further from the tin zone and out to the lead, zinc, silver zone. The ore formation in that carbonate replacement deposit is water rock interaction. So heating is another process that can occur, and it generally doesn't produce ore, but there are some minerals that can precipitate on heating. Carbonate minerals, so calcite, can precipitate during heating, and hydrite can precipitate during heating. So there are some calcium-bearing phases that like to precipitate as temperatures go up. They have what we call retrograde solubility. Even quartz has retrograde solubility at a small window between about 300 and 350 degrees. So sometimes heating will cause minerals to dissolve, but sometimes it causes them to precipitate. Now, we looked at Las Bambas at the start of the talk. So this is Las Bambas again, and that is an example of water rock interaction where an acid fluid has reacted with limestone. So limestone plus acid goes to make carbonic acid and liberates calcium. The thing here is it's using up acid. This hydrogen ion is your acidity. And the higher the hydrogen ion concentration, the more acid the fluid. So a chemical reaction that consumes acid causes dissolution of calcite and neutralization of pH. So here's a couple of chemical reactions. We have magnetite and we have chalcopyrite. iron moving as a salt complex, precipitating magnetite. And you see here, pH is on the opposite side of the reaction. So when you decrease the pH due to this reaction, it actually drives this reaction to that side as that reaction tries to make acid to counteract the loss of acid by this chemical reaction. The same here for a chalcopyrite deposition reaction. We've got iron and copper coming together. We need some sulfur. Redox is involved. But again, we're making acid and it's trying to counterbalance this loss of acid. So that chemical reaction will be driven to the right due to this widespread dissolution of carbon. That's sort of why we have to worry about writing chemical reactions when understanding ore forming processes. So if you can write a balanced chemical reaction, it helps you do thought experiments about how ores might precipitate. So it is good to have a bit of chemistry as a geologist. It's good to be embracing of geochemistry if you want to understand ore formation. Okay, we did look at this a variation of this diagram earlier, so I probably won't brood on that. What I want to show here is a different type of water rock interaction. In this case, we've got a rock that contained magnetite and hematite, and it's getting converted to pyrite. Okay, so that process can be very good for producing gold. And this pyrite is gold bearing. And in these cases, this is a scanning electron microscope image of gold, of pyrite and pyrrhotite grains. And then these are laser ablation chemical maps showing you where the gold sits. It's inside the pyrite grains in very high concentrations. That's what these bright colors mean. There's the silver, here's the copper. It's also showing arsenic and thallium. So these elements are occurring in what we call refractory mode in those sulfides, probably forming by sorption, but basically that precipitation of pyrite can help to pull this gold out. And that's because gold sometimes moves as a sulfur complex. And so when you react magnetite with pyrite, you consume hydrogen sulfide to magnetite with hydrogen sulfide, you consume the hydrogen sulfide to make pyrite, and that loss of hydrogen sulfide causes this gold species to break down and gold precipitates. There are also reactions where you oxidize the rock mass. So in this case, this rock was an andesite and it's been altered to hematite, and that oxidation of ferrous iron to ferric iron in the rock, so iron 2+ going to iron 3+ as hematite, allows sulfate in the fluid to be reduced, and that sulfate basically makes H2S, which allows you to precipitate all this chalcopyrite and pyrite. So different chemical reactions are doing different processes that may impact on high-grade ore formation. Water rock interaction is one process that occurs in every ore deposit type that we see. I won't brood on that one because I want to get to phase separation. So I mentioned at the start, there are several different types of phase separation. One type of phase separation is when a magma is releasing fluids into the overlying crust. So this is a cartoon showing how a porphyry copper deposit might form, where a high temperature magma is releasing water and metals into a fracture mesh overlying it, and those fluids migrate to the surface. Now, water has some odd behavior in that at room temperature, we experience water as a solid phase, or in our environment, we experience it as a solid phase, as ice below 0 degrees. Between 0 and 100 degrees at atmospheric pressure, we see water as steam and liquid. Now, water can, at higher pressures, keep you in a gas and a liquid phase to about 374 degrees. And above that, it exists as what we call a supercritical fluid. Now, when we study ore deposits, we often look at fluid inclusions. And if we take fluid inclusions, little pockets of fluid trapped in the quartz at depth, the fluid inclusions we take from down in these greater depths are supercritical fluids. And they look like this at room temperature. They are a single phase fluid that is stable at high temperature and pressure. As that fluid migrates up through the fracture mesh, it can, as it experiences lower and lower pressure because of less rock overlying it, it physically splits into a brine. So these are waters with very high salinity. That's a halite crystal. That's a sylvite crystal. This fluid inclusion, the fluid has about 78% salt. So these are the saltiest fluids we see on the planet being produced by this process. And that brine coexists with a low density gas. Okay, and the gas is actually the dominant fluid produced by this process. So this is what we call unmixing. And we know in a number of porphyry deposits, this transition from super to subcritical fluids has proven very important at driving ore formation, or is at least involved in ore formation. So now I've shown you a schematic cartoon of a magmatic hydrothermal system where fluids are coming from a granite. I thought I would show you the metal zoning we see above that granite. And that's because the brine tends to be localized here around the top of the intrusion. So this is our salty brine. We see high copper, we're going to see high gold, high molybdenum. And then we have our vapor, which carries acid gases. It carries sulfur dioxide, it carries hydrogen sulfide, hydrochloric acid, and this makes for more acidic fluids as we migrate up into the shallow crust. Those fluids cause this type of geochemical anomalism as we migrate from where the magmas have released their fluids and produced high-grade ore into the spent fluid that goes up into the shallow crust and may produce advanced argillic and silicic alteration at shallow levels. So these are the type of metals we see. And what's going on here is it's a combination of cooling and acidification. Okay, so in this environment, we've got decreasing temperature, decreasing pressure, and pH is getting lower as well. And so these metals are precipitating, and they generally are coming out in these sort of concentrations in the altered rocks above the intrusion. Okay? And that's because a lot of these elements move as this weird chemical species we call oxyanions. Sulfate is an oxyanion, for example. There's also a bunch of rocks on the side where fluids migrate outwards and we get water-rock interaction and we produce what we call propylitic alteration. So while the fluids are cooling here, reaction with feldspathic rocks or carbonate rocks causes the pH to increase. So we get a different pattern of metal zoning on the sides around the ore body as we do going above the ore body. Okay, so those metals, there's our proximal pathfinders, and on the sides, we tend to see these elements that might be moving as chloride complexes, particularly manganese, zinc, lead, silver, and gold. These can also be present, but they may not be moving as chloride complexes. So understanding the zoning patterns of metals around ore deposits, these are things we use for exploration. We need to understand these chemical processes to work through. All right, so probably my favorite process that occurs is boiling. And I love it because you can go to active geothermal systems and just watch it happen in front of your eyes. This is a photo of a boiling mud pool at Waitapu in New Zealand. And so we are looking at a phreatic eruption of advanced argillic altered mud coming out with steam out of this boiling acid crater. So boiling is a very important mechanism for gold deposition in the shallow crust. So epithermal deposits, which Peru has a lot of, this is a key ore forming process. It occurs because of a decrease in pressure, but it can also occur due to an increase in temperature if you place a magma into shallow water. We will see gases partition from the water phase to the steam. So we lose hydrogen sulfide and carbon dioxide to the steam. The residual water cools down because the steam carries the heat to the surface. The pH of the water can increase if the pH of the starting fluid's above about 5.5. And there's an increase in the oxidation state of the water as well. So there's a number of things going on here. And, you know, it's always fun to watch a boiling geothermal system. So this is geysering of boiling water and steam out of a hot spring at Rotorua in New Zealand. So that water is being ejected very forcefully out of this boiling spring. And it is migrated from 3 or 4 kilometres below the Earth's surface. As it comes to within a kilometre of the surface, it starts to boil and it continues boiling all the way up to where it's released here. And it takes that water about 3 or 4 days to migrate from that deepest part up the fault system to discharge at the surface. And as it rains down, the water falling on the ground is producing this sinter mound. So all of that material you are looking at there is siliceous sinter. So boiling water follows what we call the boiling point depth curve. As water starts to boil, the residual liquid cools down and the steam carries the heat to the atmosphere. So you can see the temperature decrease is gradual at depth, but as we get close to the surface, we get about 100 degrees of cooling in that upper 100 or 200 meters, depending on the CO2 content. So this is quite a gassy fluid we've drawn here. And the thing about boiling is it can produce very high-grade ore in epithermal veins. So this is a low sulfidation epithermal vein from a place called McLaughlin in California. It's bands of quartz and chalcedony and adularia. Adularia is a low temperature K feldspar, and it has these dark bands that are rich in what we call ginguru, a mixture of gold and silver and pyrite, and it has bands of free gold here. So some of the highest grade gold that we see is produced by boiling. So Porgera in Zone 7, in Papua New Guinea, Sleeper in Nevada, all this yellow material is gold. It has been produced by boiling. So locally we can get weight % gold. Normally we might mine gold at 0.5 gram per tonne. A high grade ore body is 5 grams per tonne, but you can get crazy grades of gold with boiling. Here's a chemical reaction for gold deposition. Gold moving as a bisulfide complex. We've got acidity. We've got redox. I'm writing redox here using hydrogen gas. So this is a reduced species. And I'm just using it as an indicator. We've got gold metal and hydrogen sulfide. So basically, the key process in boiling is this loss of hydrogen sulfide from the liquid. It's dissolved in water and it goes into the gas phase. And when that happens, this species breaks down and precipitates gold. So the more vigorous the boiling, the more gold you get because it's rapid. And even though there's pH changes and redox changes and temperature changes taking place that might impact on whether gold precipitates or not, the key factor here is this loss of H2S. That's our drive, the H2S going into the steam. I don't know if you've ever had the joy of visiting a geothermal hot spring, whether you have a few warm springs nearby in Lima. Sometimes they smell of rotten egg gas. And that's hydrogen sulfide coming off boiling fluids. So, yep, gold deposition from loss of H2S, very effective. Another thing that happens during boiling is we can precipitate calcite. Now, you might remember I said calcite precipitates due to heating is one possibility, but when we have very vigorous boiling, we lose carbon dioxide and that causes the pH to increase. and we precipitate out calcite. I know it seems a bit counterintuitive, but basically the pH increase caused by boiling makes calcite precipitate, and it precipitates very rapidly. So it gives us this very unusual texture we call bladed calcite. This is a rock sample about this big in my hand, and these are scanning electron microscope photos of a geothermal well, scale from the geothermal well. So we've actually put pipes into geothermal systems and brought boiling water to the surface, and we've made this form of calcite grow in those pipes. So we know boiling causes this unusual calcite texture. So when in the field, we use this as an indicator of boiling. This is a cartoon comparing a geothermal system whereby we have a fault coming up to a boiling hot spring. And here's a geothermal power station where we put a pipe in and we've brought water from deep to the surface, and we release pressure and cause the water to boil instantaneously to drive a turbine and make geothermal power. So in New Zealand, they have geothermal fluids that are carrying, the water carries about 0.2 parts per billion gold, okay, parts per billion. And we are finding on the back pressure plate here, chalcopyrite and gold and silver precipitating, and you can see 4.48% gold in that and 21% copper as we release the pressure. So an incredibly effective ore forming process, causing gold deposition about 7 orders of magnitude more concentrated than it's carried in the fluid. Over here, this is the boiling hot spring. This is silicious sinter, and the gold here is about 0.2 grams per tonne in the material precipitating up here at the surface in these little black bands. So the more vigorous the boiling, the higher grade. In a natural system, the fluids are boiling all the way to the surface, so they spread the gold out over the fault. You want to localize it to make it come out in high grades. Okay. I'm going to skip over these because I'm conscious we're running a little late. Another process that's very important is effervescence, the CO2 release from the fluid under decompression. When that happens, you also lose hydrogen sulfide, you may lose methane. So once again, this process can cause gold deposition. Champagne Pool in New Zealand, and I showed this place earlier where this gold and silver is precipitating on the edge of the hot spring. It's not a boiling spring. This is actually CO2 bubbles. This hot spring is effervescing. So effervescence is a process that's going on here. But it's most important, this process, deep in the crust. So in metamorphic environments, effervescence is common when a fault ruptures, and it produces what we call orogenic gold deposits, which you have some of these in Lima as well. Condensation, not a very common process for ore formation, but native sulfur is one thing that will precipitate due to condensation from a gas. So the sulfur is carried in a magmatic gas, and here you can see it growing around a fumarole in a volcano. There are some other elements that might move as a gas and be produced by condensation. We don't know a lot about that process. And a process that's very popular in a variety of ore forming environments is fluid mixing. It might be fluid mixing on the sea floor in massive sulfide deposits. It might be fluid mixing in breccia pipes, such as in porphyry copper and tin deposits. It might be fluid mixing along major fault systems through the Earth's crust, such as in orogenic gold. You can get very interesting chemical gradients and temperature gradients due to fluid mixing that can produce high-grade ore. It's just difficult to make fluids mix in the Earth's crust. So that's why an event such as a breccia forming or a fault rupturing is a time when fluid mixing might occur effectively. In high sulfidation epithermal environments, we have magmas releasing gases and fluids that come up to the surface. And if we have a permeable aquifer, we can have groundwater here and magmatic gas here. So we actually mix gas with water and we produce buggy quartz and advanced argillic alteration as this mixed fluid reacts with the rock mass and ultimately discharges at the Earth's surface. So you have a lot of these deposits in Peru. Peru is sort of the world premier district for high sulfidation epithermal deposits. And part of what is going on is mixing, and it's causing acidification of groundwater. And then that groundwater reacts with the rocks and is neutralized to produce this huge volume of alteration, with the gold localized in the quartz altered rocks, such as this buggy quartz you can see here. So just to wrap up, in Peru, we have magmatic hydrothermal districts. We have porphyry deposits, we have carbonate replacement and skarn deposits. That's what these red things are. They're hosted in carbonate rocks. We have high sulfidation deposits in the blue in our big advanced argillic lithocaps. We have intermediate sulfidation epithermal veins, which are equivalent to the hot springs. So having looked at all of that I just talked about, we could say, well, in porphyry copper deposits, processes that might be important to think about would be that unmixing from supercritical fluid to brine and vapor and water rock interaction. So down here, they're the processes that might be vital for high-grade ore. Go out into the carbonate rocks, and we're looking at water rock interaction being our dominant ore-forming process, but other things may occur. In the intermediate sulfidation veins and these deeper epithermal veins, boiling is going to be vital for gold deposition. And in the high sulfidation environment, it's complicated because we've got boiling, we've got fluid mixing, and we've got water rock interaction all contributing. But you can see here at different levels of the crust with different rock types, you have opportunities for different processes producing your high-grade ore. So hopefully what I've done there is given you a bit of an overview. I'm sorry if it's complicated, but just showing you a diversity of processes that might be important for metals being transported in hydrothermal systems and producing high-grade ore formation. I won't go through all the processes again, but ultimately the reason this is important to try to understand is it lets you try to build realistic models for ore formation, and that leads you to be able to develop better exploration models. And that means you may even be able to come up with new exploration targets, things that people haven't realized could form in the environment you're working with. So I encourage you to really think deeply about how ore forms. It's a pretty fundamental part of being an economic geologist and an exploration geologist. So thanks for your attention. Is there any questions? I don't think those are questions on Zoom, but I'll try to get it up for you. Hang on, I'll exit the PowerPoint. Okay. Actions. No, we're not voting. Participants, where'd the chat go? I had the chat up. Must, yeah, you're right. Chat. But I don't think the chat was about anything other than the list. So, no questions? Too complicated? Keep doing it. Okay. Thank you, Sylvia. Okay. Well, have a nice day.
Be here. Jump people.
Yeah.
Great. ¿Tienen tiempo para tomar un café?